Introduction to the rigid body rotations, motion of a spinning heavy symmetric top. Historical introduction. In this picture, we see a heavy symmetric top and we will consider its motion. Here we see a motion of a spinning heavy symmetric top. As you can see, its tip does not move and it can be considered fixed. And the top makes an approximate regular precession at the beginning, and we see some deviations from the regular precession at later stages. The top can make many different types of motion. However, it can be hard to determine the motion type by looking at the top, since its motion is fast. One can use a gyroscope instead of the heavy symmetric top to see different types of motion. In this case, the gyroscope makes the motion with cusps at the beginning, and it becomes wavy precession as time passes due to the dissipative effects. Now we see a different type of motion. The symmetry axis of the gyroscope makes loops, and the name of this motion is looping motion. There are many different types of motion of a heavy symmetric top, and we will not consider all of these in this video. Let us continue with a brief history of the top. In this picture, we see Tutankhamun's top. This top shows that the symmetric top has been known at least from the time of Tutankhamun, 14th century BC. One may wonder how humanity discovered the top at the beginning. We don't know for sure, but we can speculate. Here we see an ancient spindle used to make yarn by spinning, and these are more recent versions. The spindle is known in prehistorical times, and there is a possibility that somebody gave a spin to the spindle and observed its motion. As a result of this observation, the children had a new toy to play with, the heavy symmetric top. Now let us continue the history of the top with two more slides. This is a Hittite bas-relief showing two men. They are holding top and whips at their hands. There's another top between their feet, and it is shown in the sleeping top position. This is a part of a Renaissance artwork, which is Children's Games by Bruegel the Elder. In this part, children are shown while playing with tops by using whips. They use whips to give the lost angular momentum to the top to rotate it more. Now we will quickly review scientific developments related to the motion of a heavy symmetric top. Some of these developments are directly related and others indirectly. Most of the scientists that we will mention made many important contributions to science, and it is impossible to mention all in this video. Then we will mention only some of their contributions. Now let us consider the developments related to understand the rotational motion. As you may already know, Euclid is the person who wrote the Elements, which can be considered one of the most important works in the history of science, and it lies on the roots of many scientific developments. The Elements has 465 propositions and their proofs. Most of them are found by Pythagoreans, including Pythagoras himself, and some of them Euclid's own propositions and proofs. Apollonius of Perga wrote conics on conic sections. He defined ellipse, parabola, and hyperbola that we still use today as it is, and he gave more than 300 propositions. Here we see pages from the 9th century Arabic translation of conics. The first scientific step directly related to understand rotational motion is Archimedes' studies on the lever. According to the lever principle, the balance of moments is obtained when forces times their distances to the rotation axis are equal to each other. Force times distance to the rotation axis gives torque. However, in the lever case it is named as moment of force, and it is not considered as the change of the angular momentum, which will be discovered centuries later. To study the relation between the angular momentum and torque, humanity needed more scientific studies on the way that Archimedes opened. There's a very interesting story related to the lever principle. Let us look at Plutarchus' report. And yet even Archimedes, who was a kinsman and friend of King Hero, wrote to him that with any given power, it was possible to move any given weight. And emboldened, as we are told, by the strength of his demonstration, he declared that if there were another world and he could go to it, he could move this. Hero was astonished and begged him to put his proposition into execution and show him some great weight moved by a slight power. Archimedes therefore settled upon a three-masted merchantman of the royal fleet, and without any great effort, but quietly setting in motion with his hand a system of compound pulleys, drew her towards him smoothly and evenly, as though she were gliding through the water. This story is simplified as the well-known quote, "Give me a place to stand on, and I will move the earth." The next important step is the studies on the pendulum, and one of the first essential studies is given by Galileo Galilei. While he was in the Cathedral of Pisa, he noticed by counting his pulses that the chandelier swings in equal time intervals, independent of its amplitude. The chandelier shown in this picture is the one observed by Galileo. Later, he studied pendulums and used the pendulum for timekeeping and invented an instrument to measure pulse rate. He also studied the design of a pendulum clock. Another important contribution comes from Christian Huygens. He made very important contributions to understanding the moment of inertia while studying the physical pendulum, and these are some of the necessary steps through the understanding of rotational motion. He also constructed a pendulum clock considered by Galileo with the help of Salomon Koster. Equations describing rigid body rotations are given by Euler, which are mainly what we needed to understand rigid body rotations. By using these equations, one can explain any rotation of a rigid body. The left-hand side of these equations are components of the torque, and the first terms on the right-hand side are moments of inertia times components of angular accelerations, and the last terms are results of considering the motion in a non-inertial reference frame. Here, the torque, which is firstly defined as the moment of force by Archimedes, as we already explained, is the result of external forces. For the motion of a heavy symmetric top, it can be resulted from the gravitational force and friction force, which are crucial for explaining observations. The friction force is known from ancient times, but scientific studies do not go back that much in general. Leonardo da Vinci studied friction, but he didn't publish his results. Amontons rediscovered his finding later, but Coulomb was the person who studied and gave the basics of friction force, which are still in use today. We should note that there are more advanced recent studies on friction. However, one can still use Coulomb's law of friction, and it can be used to study the motion of a heavy symmetric top with friction in some cases. The mentioned topics can be considered as mainly related to the rigid body rotations and friction, but to understand the motion of the heavy symmetric top better, we need to know other things. Now we will give a short historical introduction to these. In fact, this is a more than 2000 years story with many interesting events, and we will give only some headlines of this story. We will focus on the developments in the scientific understanding of motion, rotations of celestial objects, and rotation itself in general. Thales can be considered the father of science, since he had tried to explain natural things with reason instead of myths and other things. Eudoxus proposed a model with Earth-centered 27 spheres for rotations of celestial objects, which are fixed stars, the sun, the moon, and planets. Some of these spheres were corresponding to epicycles. His model is one of the first scientific models. Aristotle further developed Eudoxus' model into 55 spheres. He explained the motion with the nature of the objects according to the ancient view that there are 4 different types of elements: earth, water, air, and fire, and he presented the thought that heavier objects fall faster. Aristarchus stated that the rotation of celestial objects can be explained by considering Earth's rotation in a heliocentric model. However, his views were not accepted for centuries, and some of his followers were punished by being accused of heresy. Hipparchus discovered the precession of equinoxes, which indicates the change of the polar star or Polaris. He did this by studying centuries-old observation records. Ptolemy wrote a new model for the rotations of the celestial objects. In his model, the center is not the Earth, but a point between the Sun and the Earth. Alhazen showed inconsistencies in the Ptolemaic model. This picture is from Hevelius' Selenographia, and it shows Alhazen together with Galileo. Alhazen is shown on the left, and he represents reasoning, and Galileo represents observational or experimental evidence with his telescope. Biruni stated that astronomical observations can also be explained by the rotation of the Earth, and he also stated that there are further problems in the Ptolemaic model. El-Kazini is the first person who stated that gravitational force is toward the center of the Earth. He was a slave, and his master let him be educated by Ömer Hayyam after seeing his intelligence. Copernicus wrote his famous work explaining the motions of celestial objects with a heliocentric model considering rotations in the circular orbits. But humanity needed concrete evidence to accept the rotation of the Earth, which would be available nearly 2 centuries later from Copernicus' work. This evidence is provided by Galileo Galilei. He observed planets and moons, and obtained necessary evidence for the heliocentric model and represented humanity. He also studied the motion of the small objects under the gravitation and obtained GT²/2 formula. And he falsified the old thought heavier objects fall faster than the lighter ones. He also separated the motion under gravitation into components, which is crucial for understanding motion. Alhazen also used separation into components. However, he did it for light rays. Kepler made observations and studied the observational data for years and obtained 3 laws, which are known as Kepler's laws, and showed that planets follow elliptic orbits. Descartes invented the Cartesian coordinate system, which makes it possible to do calculations easier. Newton wrote Principia and gave laws of motion. Descartes had also written laws of motion. However, his laws were not successful as Newton's laws in explaining motion. With Newton's 3 laws, the necessary calculations in mechanics can be done, which is an important step in understanding of nature. Newton also showed that elliptic orbits can originate from the inverse square law, which was one of the most important problems at that time, and Edmund Halley convinced Newton to publish his findings. Calculation in mechanics by Newton's method can be messy due to its vectorial structure, and scientists were trying to find other methods. Lagrange invented Lagrangian and wrote Lagrange equations, which is based on Bernoulli's and Euler's works. With Lagrange technique, calculations become much easier. Lagrange also studied the motion of a heavy symmetric top and invented the cross product. Another important contribution comes from Gauss, who developed the Gauss method to determine the position of Ceres. He made many other contributions to science, as it is well known. Later, his method opened the way for different discoveries. Another scientist, approaching the mechanics from a different perspective, was Leibniz. He tried to explain the motion with vis via, or living force. It is twice the modern definition of kinetic energy, and the diversity is related to difference in definitions. We needed studies of other scientists to get a better form of Leibniz's study. Johann and Daniel Bernoulli studied the law of conservation of vis via. Émile du Châtelet proposed and tested the hypothesis of conservation of total energy by dropping balls from different heights. But the discovery of the conservation of energy, which is one of the most basic laws of nature, required studies by many scientists, including the works of Smeaton, Playfair, Lavoisier, Laplace, Young, Coriolis, Pensolot, Rankine, and others. Noether discovered the relation between symmetry and conserved quantity and wrote a theorem known as Noether's theorem, which can be stated as: if a system has a continuous symmetry property, then there are corresponding quantities whose values are conserved in time, in simplified terms. Now we will shortly mention the invention of the gyroscope. The first version of the gyroscope is developed by Johann Friedrich von Bohnenberger. Later, Laplace asked Foucault to make a gyroscope, and he made one of the most known versions of the gyroscope, which can be used to detect the rotation of the Earth by using the conservation of angular momentum. And the name gyroscope is given by Foucault, considering the Greek words gyros meaning rotation and scope meaning to look. Our final topic is the studies related to the motion of the heavy symmetric top. Root gave a classification for different types of motion of a heavy symmetric top. Klein and Sommerfeld studied also different types of motion and other properties of the top. Shellet wrote a mathematical model for the rise of the top. Many other scientists have studied the motion of a heavy symmetric top. It is not possible to mention all of them here, and interested readers can look at related scientific works. Some of that will be considered later. Thanks to these scientists, we are able to understand better. You can find references for pictures in the explanations of the video. Thanks for watching.